it doesn't work. So in the meanwhile, I will introduce myself. So I'm Andrea Araldo, and I'm associate professor at Telecom Sud Paris. And I'm going to talk about managing the cloud to edge computing continuous under uncertainty via AI with performance guarantees. Okay, so this is the picture I will have into my mind during this talk. On the one hand, we have users willing to consume services by sending requests to some service providers like Netflix, who provides streaming services. Usually, these services are deployed in the cloud, but there is a limit. So the cloud is physically far from end users. So there is a latency below which we cannot go. So this is a barrier to the development of new types of applications like augmented reality or virtual reality or high-resolution online gaming, etc. So to enable these new applications and to solve this barrier, we believe that network operators are the key. So network operators like Orange or AT&T are the only ones who have a very widespread infrastructure that goes up to the edge, very close to the users. So they are the only ones who can enable low latency applications. So they could virtualize their infrastructure and let third-party service providers deploy their services there. So they could become a sort of cloud providers plus. They could monetize this, even if they don't do it now. And maybe there are many reasons we can discuss about. In any case, to enable this kind of new ways of using the network infrastructure, there are many problems to be solved, on which I worked with many colleagues. And so I will give a panorama of this work. So first problem is an economic problem. So deploying computing capabilities all across the network costs a lot of investment. And so we should find some ways of invest or co-invest together, network operators together with service providers in order to have a safe investment, return of investment with high likelihood, despite the uncertainty about the future. This is the first problem. Another problem is placement of these services. Another problem is resource allocation. Another is routing. And finally, pricing. So today I will just touch upon 1 and 2. So let's start with the first. And I will talk about a joint work with INRIA, Nokia Bell Labs. And I'm not the main contributor. It's far from that, but I like this work, so this is why I'm presenting it. So we focus in this work on machine learning applications. So you know that whenever you want to provide an inference, for instance, a classification, you can use many types of models which have different complexity, different resource utilization, and at the same time, different accuracy. So the question we ask ourselves is, given that we have available all these models, which ones we should deploy and in which nodes? Okay, so the general setting is this one, in which, again, we take into account the infrastructure of a network operator, and we assume we have third-party applications that need some machine learning inference. For instance, we have conversational agent application that needs speech recognition, augmented reality that needs objects recognition, and so on and so forth. And we want to understand how to place the models in the cloud to edge continuum, and also which versions of this model, the small ones, the big ones that are more precise but more resource incentive, and so on and so forth. And we want to do it for the different application providers that should coexist in the same physical infrastructure. So to solve this decision problem, we use online learning. So we provide an algorithm that is based on subgradients. descent. And our goal is to minimize cost, which is a combination of inaccuracy costs and latency cost. I will not give the detail of the algorithm. I will just give the results. So first, an analytical result. So we can show that our algorithm has a regret that grows sublinearly as a square root of t, meaning that the difference with respect to a theoretical oracle that knows everyone, that knows all the requests from users, becomes smaller and smaller very fast. And this is confirmed also by the numerical results. Here we compare our algorithm with the theoretical oracle that knows everyone, everything, all the requests now and in the future. And we see that we are very close, both in terms of latency and inaccuracy. So despite knowing nothing about the future, we can approach a theoretical oracle. Second example is about resource allocation. This time we focus on one node, one edge node, and our goal is to partition its resource, we consider storage, and to allocate each slice to one of the third-party service providers. You can imagine on the right Netflix, YouTube, or others. So users request content. If the content is into the edge node, it can be served directly. Otherwise, requests have to go through the internet to the central location of service providers, generating upstream traffic, which is costly for the network operator. And this is what we want to minimize. To do so, we set up a closed loop approach based on reinforcement learning. So you might imagine, okay, for sure you will use deep reinforcement learning because it's state of the art. Well, we don't, because we can't. So in deep reinforcement learning, you need long training phase, and you need a lot of examples. We cannot afford that because we assume that we are running our algorithm on a system that is up and running. So we do not have any previous phase in which we can perform training. We have to take good decisions directly on a hot system. And also, we don't have a lot of examples because we cannot perturb the allocation of the system many times. Otherwise, the system will not work properly. So we can perturb only maybe 4 times a second. And so we collect 4 experiences a second, which is definitely not enough to train a deep reinforcement learning algorithm. So we do something a bit simpler. And we propose to use model-based reinforcement learning, model-based QLearning, actually. So I will not go into the detail, but the basic observation is that we can decompose the cost of our system into 2 parts. One part that is stochastic and depends on the state, on the allocation, and one part that is deterministic and depends on our actions, how we change the allocation. So we can focus on this stochastic part and train a supervised model to model this part. This allows us to, instead of considering the actual cost, to consider a simulated cost that comes from this model of the true cost. So the advantage of having this sort of virtual cost is that instead of updating our Q table 4 times a second based on true experiences, we can train our algorithm on virtual experiences that come from the model. So we can make how many updates we want. For instance, we do 200 updates per second. So we accelerate learning. And I go directly to the results. And we see that if we measure the cost, our algorithm is the black solid line. And you see that after only 40 minutes, we go close to the optimal theoretical cost. And we also have theoretical guarantees. We can show that our allocation goes to the optimal one and stays there without perturbation, without further modifications, with probability 1. So to conclude, AI is an effective set of tools to manage cloud-to-edge continuum, because it gives good practical performance and also analytical guarantees, and also is computational efficient finally. But a concern that I want to share with you is that nowadays AI is deep learning. So every time, at least in my experience, I try to submit a paper or to show an idea, the answer is always, why don't you compare with deep learning? So we know that deep learning is hard to train, hard to tune. So if in front of me, I have always this barrier of having to pass through the pain of deep learning, even if I'm proposing another idea, I think the risk is that deep learning becomes a barrier more than something good for us. So I don't know if you had the same experience, but I wanted just to share with you this. And this finished my talk. Thank you.
Thanks. So you mentioned comparison to optimal, but you didn't really define optimal. Is it the offline optimal, or so where it assumes that you have access to the arrivals? That's, I mean, how long it stays in, which may or may not be a fair comparison, right? Because if it's the offline, sometimes you may not even be able to achieve that optimal, or is it some other form of optimal?
Yeah, that is the optimal, and it's a theoretic, it's an ideal comparison. Of course, this cannot be achieved in reality. So we want to see how close we are with this ideal baseline.
I have a second question. I'll jump in. So I appreciate that you couldn't use deep learning, and I understand the reason why. But even with reinforcement learning, you're sort of dependent on some stability. In order to learn, the patterns that you're observing have to repeat, right? And in the edge computing environment, things are changing pretty fast. So I guess have you?
Yes.
How quickly does it recover from a drastic change in?
Yes. So I didn't put the result here, but it's in the main publication, and we try to see what happens. What happens if the load is non-stationary? It varies, and we see that the algorithm adapts quite fast because you see that the convergence is very fast. So if something changes, there will be a moment, maybe 30 minutes of suboptimality, but then we catch again the good allocation. Thanks.
So I didn't really understand what you were trying to say about, why you're not addressing sort of running large language models or even, these kinds of the new AI models, because all of the framework that you set up could be applied to this new world we're living in. And it seems like the problem's even bigger if you're focusing not, on large language models, or there'll even be personalized smaller models that are going to be running at the edge, all the personal digital assistants that everyone's thinking about, right? Those are very heavy requirements that are going to be sitting at the edge. So is that an application area for what you're talking about here? Or?
So in the first work, yes, we can assume that these models are maybe language models. But if you want to deploy these in edge nodes, for instance, base stations, or even access points in the house of people, you cannot afford like having a big GPU with a lot of memory, etc. So you have to be content with smaller versions of these models that are maybe a bit imprecise, but that you can deploy close to the users. So there is a trade-off between precision and latency. And there are techniques such as distillation, in which you can take a big model and translate it into small models. So now you have a lot of choice, and it's up to you to decide if you are more interested in low latency or high precision. And you can play with that, and we wanted to play with that in this work.
Yeah, maybe I think the comparison with deep model is since you have no data, hardly any data
Yes.
to train, and these models are successful when they have massive amount of data.
Yes.
The point it does not apply in the same type of data sets.
Exactly. But still,
No.
the reviewer.
Yeah,
I'm sure.
I think it does not. Now, there's another class of methods which is probably closer to what you have, which are Bayesian optimization methods, in which you basically approximately function close to the minimum that you're obtaining.
Yes.
All methods,
Yes.
essentially. So have you tried something like that? So which
Yes.
is more black box kind of things. It's less, but which is precisely tailored to the case where you have very few data to. You need to take decision on the fly while you are optimizing
Yes.
your.
Yes, these are examples of methods we could use. So I've used Bayesian optimization for other work. I work also in transport networks, and there you have problems that are mainly offline. You have to design a network, and every time you want to evaluate a point, it takes a long time. So you can use Bayesian optimization. But for offline problems, here we want to take decisions every half a second. So I feel that Bayesian optimization might not be the right answer, because also Bayesian optimization jumps from an allocation to another. Because you are offline, you can test whatever you want. But in a real system, if you change one allocation to the opposite one, you are breaking your system. So you need something that takes into account this switching.
Recent work addresses that, right?
Okay.
It's true. I agree for the static case, but the more recent way is precisely to try to do online to decide whether I should keep the measurements, remove the measurement because it's stale, because otherwise it does not follow. And so there are more recent works that might be of interest.
I should look into them. Yeah, thank you.